Hi, my name is Shivam. I am from Institute of Engineering and Management, Kolkata. I am a student of second year Computer Science and Engineering.
Hi, my name is Royal Kumar, a second year student of Computer Science and Engineering from Institute of Engineering and Management, Salt Lake.
Hi, my name is Prasann Kumar. I am a student of Institute of Engineering and Management, Kolkata. I am a student of second year CSE branch.
Hi, my name is Boni Purojit. I am from Institute of Engineering and Management, Kolkata. I am of CSE branch, second year.
And we are group Provost 004.
Planet Earth is seemingly awash with water, but how much accessible fresh water is there? Only 2.5% of all water on Earth is fresh water, and more than 96% is salt water. Of this 2.5% of fresh water, more than 68% is frozen as snow and ice, and more than one third is stored below ground as groundwater. This means that only 0.3% of all fresh water on the planet is readily available as surface water. It is remarkable to think that the global population and all living species are supported by such a small amount of water on the planet. For how much longer will this be the case? 2 lakh Indians die every year due to inadequate access to safe water. And India's water crisis is only getting worse. Leaving 600 million Indians to face severe water shortage, India is currently ranked 120 among 122 countries in the Water Quality Index. By 2030, India's water demand will be twice the available supply, and 40% of the population won't have access to drinking water, which may lead to a 6% loss in the country's GDP. Groundwater accounts for 40% of India's water supply, and that's depleting at unsustainable rates. By 2020, 21 major cities will run out of groundwater, according to Composite Water Index scores FY17. Previously drought-stricken states have managed their water resource better. But 50% of India's population is concentrated in the worst performing states. Cities have a very complex water distribution and pipeline system, with thousands of miles of water pipes carrying water underground, reaching every place of requirement. And the aging infrastructure results in ever increasing leakages and pipe bursts. 32 billion cubic meters of water are estimated to be lost each year through leakages. Also, billions of rupees are spent on repairing bursts, and we also have an inadequate leakage detection system due to aging infrastructure, rapid population growth, declining water source quality, and water scarcity. So, we see an increasing pressure to improve operational efficiency and reduce reliance on manually intensive processes. For example, visiting pressure regulating chambers to check pressure and asset condition or change settings also drives up operational expense, and replacing pressure pipes requires large capital investment and is disruptive. Also, the current water distribution and sanitation systems will be unable to keep up with the population's demands, deeming it to be inadequate and old. For example, more people means more water used for personal hygiene, with 10 to 25 gallons of water used for shower and up to 70 gallons per bath takes lots to keep clean. Also, greater populations means more clothing and more laundry. So, let's have a look at the objectives of the project Intelligent Water Distribution System InWaDis. The main objective is to facilitate the implementation of the new asset management system. WSN will leverage widely on condition assessment technologies to retrieve more dynamic and real-time data. The proposed solution detects the leakage in the water distribution using a system which is intelligent enough to rule out the corner case developed during extensive water usage, thus making the case of water leakage crystal clear. A solenoid valve is provided in the system in order to cut down the water supply by closing the valve in case of heavy leakage. This will result in reducing the huge amount of financial wastage involved in fixing pipe bursts and leakages. The goal is to minimize the wastage of water at the root level of consumption through controlled and checked water supply at every level of requirement, be it household, commercial, or ornamental use. InWaDis will also serve in the underground transfer of water from areas having abundant water to areas facing acute water shortage by analyzing the pressure sensor graphs for every locality. As a byproduct of the above goals, InWaDis can prove of much greater help, like this system can be applied in irrigation field where humidity sensor and temperature sensor can be made use of, thereby ensuring an adequate amount of water supply to the crops. Flood conditions can also be mitigated by directing the extra amount of water from dams directly to areas facing water scarcity. Now let's have a look at the tools and parameters used. IoT tools. Now to get the pressure difference at each water junction, water pressure sensors are used to get the water pressure at each junction. The flow rate sensor is fitted at each pumping station near the buildings to calculate the usage of water by families of each house. In order to send the data received from the pressure sensors and the flow rate sensors, a Raspberry Pi, which is very small computer, is used. Pressure sensors are unable to detect any leakage with 100% precision because they are dealing with thousands of meters of pipes of water. So for this case, we use current sensor modules which detect any current on the outer wire and thus shows there is any leakage. But without internet connection, we are unable to send the data to the cloud. Therefore, we use GSM module for the connectivity. Tools used in data analytics. Since the data point is recorded on a minute basis, so it is huge, and despite being discrete and regular, these data points seem continuous when plotted. This real-time data leads to data explosion. The data being generated at very high speed and volume requires a cost-effective and innovative solution for storing and analyzing. With the ever-increasing population, we need to deal with ever-increasing bulk data. Hadoop ecosystem contains many components like HDFS, MapReduce, Yarn, and Common, which serve a broad spectrum of applications. On analyzing the precision of different ML algorithms on the data we recorded, linear regression algorithm proved to be the best fit for our data points, with the highest accuracy among all the other algorithms. This algorithm is based on supervised learning. Also, we need a framework to implement this algorithm. So we use TensorFlow, which is an open source computation library used for creating applications that require high-end numerical computations. So with this objective, let's have a look at the proposed solution with each step in detail. Drinking water travels directly from reservoirs to different areas through branch of pipes with the help of gravity and pressurized beams. Different diameters of pipes are used at different places by noticing the water fluctuation levels. Different sensors are fitted at each junction of flow to measure different parameters like pressure difference, leakage, and flow rate. Flow rate sensors are only used at the pumping chamber outside the house to measure the usage of water by different families in the building. It has rotational device inside such as propeller or paddle wheel. The faster paddle is rotating, the more flowing through the pipe, which in turn sends a graduated signal to the PLC. Pressure sensors are used at every junctions of the branching. In a nutshell, it converts the pressure to a small electrical signal that is transmitted and displayed. Pressure sensors are fitted at each junction for pressure data and calculating pressure difference between two junctions. If the pressure difference data shows a critical change, then it will be alarming condition to work upon. It will happen when pipe bursts. When current sensor module is basically used to detect any leakages in the pipe. Here we are using electric conducting property of water to detect leakage. In this system, two wires are used between two junctions. One wire is placed inside the pipe and another wire is covered outside the pipe in a solenoidal form. The pipes are insulated so that the wire outside the pipe does not hurt the outer environment or the wire does not show any unwanted current. We draw voltage difference between the two junctions at regular period. Current in the wires will be less than 0.01 milliampere so that it does not affect any human. When the circuit gets completed due to the water leakage, then there is current detection and we know there is a leakage. Sensors are connected to Raspberry Pi which sends data to the cloud. But to send the data, we need communication system. Therefore, we use GSM module for the communication. Centralized control system works upon the data that are sent to the cloud. Let's see how Hadoop helps in dealing with the big data. Hadoop consists of three layers: HDFS, MapReduce, and the third one is YARN. The storage layer, HDFS, Hadoop Distributed File System, provides for the storage of Hadoop. It stores the data in a distributed manner. The files get divided into a number of blocks which spreads across the cluster of commodity hardware. MapReduce. It divides the tasks submitted by the user into a number of independent subtasks, which works in parallel to increase throughput. YARN, yet another resource manager, looks after the allocation of the resources among various slaves competing for it. There are two daemons running for YARN. One is node manager on the slave machines, and the other is the resource manager on the master node. In short, the client first submits the data and program. HDFS stores that data, and MapReduce processes that data. Now let's see how linear regression works on this data. Here is an example of the pressure data we had from the water mains at the junction of a locality and the pumping station of every building. The pressure gradient per minute is recorded based on the data received from every junction. The data is recorded daily for about a month and for 24 hours a day. Linear regression proved to be the best fit, with highest accuracy among all other algorithms based on the data points we had.
Linear regression attempts to model the relationship between two variables by fitting a linear equation to the observed data. One variable is considered to be an explanatory variable, while the other is considered to be a dependent variable. So you can think of linear regression as the line of best fit. So the line of best fit can be represented by the linear equation y equals a plus bx, or y equals mx plus b, or y equals b subset 0 plus b subset 1 times x. You mostly learned this in school. So b is the intercept. If you increase this variable, the intercept moves up or down along the y-axis. And m is the slope or gradient. If you change this, then the line rotates along the intercept. So data is actually a series of x and y observations as shown on the scatter plot. They don't follow a straight line. However, they do follow a linear pattern, hence the term linear regression. Assuming that we already have the best fit line, we can calculate the error term epsilon, also known as the residual. And this is the term that we would like to minimize along all the points in the data series.
Based on the data points we would get, x-axis would be our time axis and the pressure difference would be on the y-axis. The graph we got has an intercept of about 99 psi and a slope of 0.06. The flow rate sensor at the pumping chamber of every building senses the rate at which water is flowing up to the tank of the building per minute every day for 24 hours a day. This data is utilized to find the amount of water consumption per household or industry in the area. This data is used to find the change in the water consumption in different areas and thus allows us to make a balance between areas of different water requirements. And now, we use scikit-learn library to import the linear regression model and implement it using TensorFlow. TensorFlow has APIs like Estimator which provides high-level abstraction to build machine learning applications. In this system, we build the linear regression model using low-level TensorFlow in the lazy execution mode. DAG keeps track of all the computations and then executes all the computations done inside a TensorFlow session. Now we require to import certain Python libraries like NumPy for computations and Matplotlib for plotting, which will work on the big data. The dashboard is created from the data, which keeps a regular check on the pressure management, leakage management, and water consumption. When there is an abnormal condition, the alert is generated. The network alarms will operate in 3 steps now. When the data analysis shows true condition for a prolonged period of time, say 1 day, then we generate an alarm. Now on the basis of abnormality in pressure inside water channel or abrupt increase or decrease in water flow rate, then the management team checks the problem in the water distribution system like leakage or blockage or varying water usage. The maintenance team is then updated accordingly to solve the emergency condition. The automated valves at the junction of every locality and at the junction of each sector mitigates the water loss during leakages or pipe bursts, while the maintenance team responds. Each day, the distribution system delivers drinking water from the treatment plants to the customers' taps. These systems are designed to provide an uninterrupted supply of drinking water on demand, compliance with regulations in line with customer expectations, and with minimum environmental impact. Here is how and why at a glance. Drinking water travels directly from treatment plants to households via pressurized means depending on the topology. We can also pump water into high storage tanks so that the water flows through the system via gravity. The distribution networks branches out towards each user connection point. Special devices and equipments help to regulate water pressure according to fluctuating levels of consumption. Pipe diameter and material is adapted according to the local constraints and the characteristics of water. The system is managed in small zones, which makes it easier to diagnose problems, do maintenance work, and accurately measure water distribution and consumption volumes. This is how we identify water losses. Leaks are found thanks to acoustic detection technique on utilization of tracer gas. At the base of the buildings, pumping stations boost the water pressure so that it reaches every flow. We sample and analyze water throughout the network on a daily basis, making water one of the most closely monitored substances for human consumption. Measuring instruments, sensors, and probes are installed at key locations throughout the system. Meters measure water consumption at each level in the network. Other meters and instruments provide real-time readings on the flow rate, pressure, current detection, and water quality, and detect any leaks or changes as soon as they occur. These instruments transmit data via communication systems. This is what makes drinking water systems smart. All the data converges at a centralized control center. Those control centers combine and analyze the data to provide insight about the operations or events. This way, analysts have a good global view of the network in real time. This is how they can monitor water quality, improve the operation and maintenance of the system, and respond rapidly and transparently, keeping authorities and consumers in the loop. By ensuring a continuous supply of water while constantly optimizing our network performance, InWaDis is a long-term guarantee of operational efficiency for cities and for consumers. The solution looks quite complex, right? So let's look at the effectiveness of the solution. A smart water system integrates information and communication technologies into the management of the water distribution system. Sensors, meters, digital controls, and analytic tools are used to automate, monitor, and control the transmission and distribution of water, ensuring that the water is efficiently delivered only when and where is needed and with good quality. Implementation of InWaDis will also streamline manpower requirements and redesign work processes by automating mental tasks. Decision support tools such as predictive hydraulic modeling, valve operation simulation, demand prediction modeling, and pipeline failure analysis help to improve network assessments and planning. With sensors and analytic tools deployed area-wide to provide a real-time monitoring and decision support system, the InWaDis enables water system network to manage the water supply network efficiently, ensuring that all people will continue to enjoy reliable and sustainable water supply for generations to come. We have highlighted WSN's vision for the following key aspects of the InWaDis in relation to both the network system and customer end. With improved asset management, effective preventive maintenance of high-risk pipes will further reduce the number of leaks. In tandem, as the networks of real-time pressure and water quality sensors continue to be expanded, WSN will also be equipped with the necessary data and tools for timely incident management. At the customer's end, real-time water consumption information from the automated meter readings will help customers to make informed choices towards water conservation within their homes and company premises. The technology roadmap for each aspect of the InWaDis follows a common theme: the adoption of real-time sensing methods and data analytical tools as ICT and analytical software solutions mature and new technologies emerge to better meet with the needs of water utilities and customers. So how will the experience of end user improve? Now the people can get water at the taps at required pressure and good quality without waiting for the good pressure of water. They will get 24/7 water since the leakage detection will be quick. In the place of scarcity of water, the places having abundant water will be transferred to the scarcity of water. What is the approximate cost of the solution? Flow rate sensor in the market is 650 to 750, so we take the average as 700. Current sensor module is between 280 to 320, so we took the average to be 300. Water pipes are also insulated, and for 100-meter pipes, the cost came out to be 10K. The cost of pressure sensor is between 700 to 750, so we took the average to be 725. The cost of GSM module was between 950 to 1050, so we took the average to be 1000. Raspberry Pi was between 2800 and 3000, so we took the average to be 3000. Finally, the total average cost of one whole system between two junctions is around 16,000 rupees. Now let's see how much can we save from this solution. We use flow rate sensor at the pipe chamber near the house to measure the usage of the building. Leakage sensors are not used because they cost 90,000 rupees. In case of pipe burst, leakage sensors will be destroyed. So in place we use wired system to take the leakage, by which we save 70,000 rupees. Using Raspberry Pi 3, we save 1000 rupees in comparison to other Raspberry Pi. We are using GSM module for the connectivity at the place of Wi-Fi. We must supply internet connectivity always to the Raspberry Pi to send the data.